Okay, last video on chapter 3 and 17. Just two problems here, and they both deal with the same concept that when you have two objects in contact with each other, they translate heat energy through particle collisions, but eventually they're going to reach thermal equilibrium. Okay, so first type of question. Suppose we have 54 grams of a metal, and we have a calorimeter that has 200 grams of water in it at, let's say, 20.6 degrees Celsius. We put our metal in a hot bath and we heat it to 99.2 degrees Celsius. Okay. When I pour the metal into the water, into the calorimeter, the temperature of the water increases. So that's right after mixing. The temperature of the calorimeter water, it goes up to 23.4 degrees C. I want to know, what is the specific heat of the metal? Alright, so two concepts here. One, when they get poured together, their final temperature is going to be the same. So the final temperature of the metal, so we'll write this, T final for the metal is going to be equal to T final for the water in the calorimeter. So that's one concept. Second concept is that the water in the calorimeter gains heat and the metal loses heat. Now, how much heat the metal loses is equal to the amount that the water gains. So we're going to use that fact to help us figure out the specific heat of the metal. So let's examine Q gained first. Q gained by the water in the calorimeter. All right, so we know Q is equal to M delta Tc. And for the water, we're dealing with 200 grams of water. And the temperature goes up to 23.4, starts out at 20.6, so T final minus T initial, times the specific heat of water, which is 4.184 joules per gram degree C. So we can calculate how much energy the water gains. 200 times 2.8 times 4.184, and we get 2,343. So 2,340 joules. All right. So that's going to be equal to negative Q lost. And the energy is lost by the metal. So we can set this up that the opposite of the amount of heat lost is going to be M delta T, C of the metal. So we want to solve for specific heat of the metal. So negative Q over M times delta T. So now we can substitute in. So this is going to be negative 2,340 joules. The mass of the metal was 54 grams. Was it? Yeah, 54.0. T final minus T initial. So T final is 23.4. And the initial temperature was 99.2. So it'd be 54 times 75.8. And that comes out to be negative 4,090. All right, so now we can just simplify this. And I get a specific heat of 0.572 joules per gram degree C. So that's the specific heat of the metal. So the type of problem where as long as we know that we're pouring them together, that their final temperatures are going to be the same because they're in contact with each other, that the heat gained by the water is equal to the heat lost by the metal. Second type of problem, water mixtures. Suppose we take 51.6 grams of water at 42.6 degrees Celsius, and we're going to mix it with 131.2 grams of water, which is at 18.2 degrees Celsius. So when we mix them, we know that one T final of the hot water is going to be equal to T final of the cold water. So they're going to give you a question like this, and they're going to say, what is the final temperature of the mixture? Well, we don't know the final temperature, so I'm going to call this X. So T final for the hot water is going to be equal to X, so is T final for the cold water. So we can set this up. Q gained, now what gains the heat? The cold water. Is going to be equal to negative Q lost. What loses the heat? The hot water. Alright, so let's set up an equation here. M for the hot water times delta T times C. So again, everything on the left side of the equation, has to do with the cold water, not the hot water. And everything on the right side, we're going to do negative M delta T C. But everything on the right side is going to deal with the hot water. Alright, so let's substitute in some values here. Do the hot water in red. We have 131.2 degrees C. And then our T final is 18.2. Our T initial, we're dealing with the cold water. My bad. T final then is X. We don't know what T final is, but our initial temperature is 18.2 degrees C, and the specific heat of water is 4.184 joules per gram degree C. We're going to set that equal to the hot system. Really? The hot system is going to be negative M 51.6 grams. And then T final is X. T initial is 42.6 degrees C. And the specific heat is 4.184 joules per gram degree C. Alright, so now we can simplify this. We're going to do 131.2 times X times 4.184. I'm just distributing this, and that gives me 548.9, and that's going to be, we're going to eliminate the units here. It'd be joules per gram, but we're going to eliminate the units. Times X minus 131.2 times 18.2 times 4.184, we get 9,991. And that's going to be equal to negative, I'm going to simplify the other side, 51.6 times X times 4.184. It's going to give me 215.9 times X minus 51.6 times 42.6 times 4.184 gives me 9,197. Alright, so now we can combine like terms. I'm going to distribute that negative first. Alright, got to get all my x's on one side, so I'm going to add 215.9x to both sides. And then I'm going to add 9,991 to both sides. And now I'm going to solve for x. And that gives me a reasonable 25.09 degrees C. All right. So now do understand that this particular question, dealing with the water mixes, this is extra credit. This is considered honors level, so it will only be offered as extra credit on your next test. And then the one with the metals, this was done in the lab, so this will definitely show up on your next test. So Q gained versus Q lost. Thank you very much.